Hello everyone, welcome to another video on this channel, and I'm going to try a new kind of video, which is going to look back on a historical severe weather event here in the southeastern US. This is going to be a tornado review, or case study if you will, on the Airport Road F4 tornado in Huntsville, Alabama, back on November 15th, 1989. So this is a poster put out by the National Weather Service, and they give a pretty nice overview of what this tornado was about and the event as a whole. So you've got some of the survey details from this tornado, some damage photos, or not damage photos, photos of the tornado itself, and then some of the forecasts put out ahead of this rate to help raise awareness, and some of the damage photos left in this tornado's wake. And so on this video, we're going to take a more in-depth look at the ingredients that came together for this event, discuss the warning process for this day, and then talk about how this tornado came to fruition. So if you enjoyed this video, leave a like and subscribe, and we're going to get started. So I'll start off with some general stats from this event. So this event occurred over 3 different days, November the 15th through the 17th, and there were a total of 40 tornadoes from this event. 18 of them were on the 15th, and most of them were concentrated down here in the southeastern U.S., which is where the most intense part of the outbreak occurred. The most notable tornado was an F4 tornado that tore through Huntsville during the late afternoon. So here is the storm survey from the National Weather Service, and there were a total of 30 fatalities from this event, and 21 of them came from this one tornado, and injured over 400 more. This tornado was about a half mile wide at its peak width and tracked about 19 miles across Madison County. And so this tornado began over Redstone Arsenal and tracked directly over Airport Road, Whitesburg, and Jones Valley, which is where some of the worst damage is seen. And we're going to take a look at some of the damage photos here in just a moment. And this tornado continued to track to the northeast and lifted somewhere over near Killingsworth Cove in eastern Madison County. Along its path, hundreds of homes were damaged or destroyed, along with several other businesses and buildings destroyed. This tornado caused up to about $250 million in damage. So this is a very costly tornado. And so this tornado was at the maximum intensity was rated with wind speeds of up to around 250 miles per hour. That is a very high-end F4 tornado in the original Fujita scale, which is in fact 10 miles per hour shy of an F5. So it's a little hard to tell exactly how strong the tornado would be rated under today's enhanced Fujita scale, but most tornadoes that are on the high end EF4 range are typically rated somewhere around 190 miles per hour, and plus or minus 5. So this tornado would be on the same level as, say, Mayfield, Kentucky, or Rolling Fork, Mississippi, just to help give you an idea of exactly how strong this tornado was. So later that night, this was not the only significant tornado to occur. There was another notable tornado, an F3 tornado, in northeastern Georgia. You can see here. And this tornado, indicated by the storm survey, was estimated to be about a half mile wide in its damage path. So that is a very large tornado to also occur in this outbreak. So now let's look at some of the damage photos left in this tornado's wake. So most of these photos are going to come from either the Weather Service or the Huntsville Times. And so we're going to take a look at some of the damage photos from Jones Valley. And you can see this is what was left of Jones Valley Elementary School, which was basically nothing. I mean, this school was pretty much demolished by this tornado, which Jones Valley again took a direct hit from this tornado. So this is a very powerful, very destructive tornado, and actually it's a miracle that there were people that survived this, which is pretty incredible. Here's another picture of a neighborhood. I'm guessing this is somewhere in Jones Valley. I mean, you can just see that this neighborhood is completely demolished here in the wake of this tornado. And so I'm going to take a look at a couple more damage photos. Here is an apartment complex, I believe somewhere in Huntsville. You can see some buildings fared okay up here, and then some structures not so much. You can see that there's just debris scattered everywhere. A little bit hard to tell, but maybe there was a structure here that was maybe slabbed. I don't know if that's a concrete slab or part of the road. A little bit hard to tell. We can take another look at the same apartment complex, and you can just see there's just debris scattered everywhere. And so that was a pretty common theme across much of Huntsville. In a little bit, we're going to take a look and to briefly discuss the Synoptic setup that led to this event. But first, as a side note, if there's one good thing that came from this tragedy, it's that this event started Barron Services. And so Barron Services provides weather technology to a variety of industries, such as aviation, insurance, public media, or public broadcast, public safety, and transportation as well. And so their products are tailored to their clients' needs by analyzing complex weather information. So they actually mention on their About Us page that this very tornado is what inspired their new mission, and which is delivering life-saving meteorological tools for the moments when it matters most. So that's just a little bit of history on Barron. And if you're familiar with weather or in this field of meteorology, you've probably heard of this company. So that's just a little bit of history. So now let's look at the Synoptic setup briefly. And so we have a pretty large long wave trough that is carved out through much of the continental United States. And so this trough tracked down to the southeastern U.S. and took on as neutral to maybe a slight negative tilt during the overnight hours. And so you can see this shortwave here digging down deeper into the southeastern United States. And so that's just with strong winds rounding the base of this trough. That's just indicative of a very strong storm system that was pushing through the central and eastern United States. So we look at the surface pattern as well. That's not the surface pattern. Okay, so let's check out the surface pattern here. Let's go back to the morning of the event. We have a surface low that was consolidating over the Great Lakes region, and that swept a cold front down into the southern United States. To the north, we have a warm front that is situated over southeastern Canada, and so this made for a very broad warm sector ahead of this mid-latitude cyclone, which helped set the stage for a significant severe weather event that was about to take place. This setup caught the attention of National Weather Service officials days in advance, and the warning process looked pretty similar to what it looked like today. And so that warning process is documented in their disaster survey, which of course I will include a link to this disaster survey in the description box below. And so I'll take you through some of the high points on the warning process, but I won't go through this document word for word. I'll leave a lot of that for your reading on your own. But you have the executive summary, which kind of just summarizes what happened on the 15th, and then you also have the findings and recommendations. After their storm survey, they listed their findings, and they gave some recommendations on how the warning process can be improved on the Weather Service's part and public media's part as well. Part 2 is a summary of the warning services, which I'll take you through in just a moment. Appendix A shows what the staffing looked like and the Weather Service in Huntsville. And then Appendix E is the individual accounts from ranging from a wide variety of people, including members of the public or an official meteorologist. And then down at the bottom here, we have our figures that are listed. So I'm actually going to take you through some of the figures first. Let's take a look at the severe weather outlook from the National Severe Storms Forecast Center, or currently known as the Storm Prediction Center. This was issued on around midnight on the 15th, and this included a moderate risk of severe weather for much of the Deep South, with a slight risk surrounding that. And then this was then later upgraded to a high risk of severe weather later that morning, and the slight risk was expanded up into the Great Lakes region, where confidence increased in destabilization further north. So these forecasters issued a public severe weather outlook, and that is mentioned in the summary of the warning services. And so here is their severe weather outlook, which mentioned an outbreak of tornadoes forecasted to develop on Wednesday across the Tennessee Valley, and described as a potentially dangerous weather situation, and encouraged people to review the weather safety plans as well as weather offices in Alabama were raising awareness for this event because they were very concerned for this significant severe weather event that was about to occur. And so around lunchtime, the National Severe Storms Forecast Center issued a tornado watch for northwest Alabama until 8 p.m., which was then later expanded to include most of the state of Alabama. This is about an hour or two before storms entered Alabama from the west. So severe thunderstorm warnings began being issued by the Weather Service for the western part of the state. And then attention then soon turned to the Huntsville area, with discrete storms maintaining themselves ahead of a squall line. And as we're going to see, the environment was pretty favorable for tornadoes across North Alabama. And the statement issued from the Weather Service included wording like, "These storms are very dangerous and not to be taken lightly. These storms should reach the Huntsville area sometime between 4 and 5 p.m. As storms crossed over I-65 around 4 o'clock, severe thunderstorm warnings was issued for Madison County at around 4:15. This was then later upgraded to a tornado warning by 4:35 after receiving reports of a tornado on the ground. And so, as the supercell tracked across Madison County, the Weather Service continued the tornado warning past 5 p.m. for Madison and Jackson counties. And then the severe weather threat continued for northeast Alabama until around 6:30 or 7 o'clock, once the tornado watch was canceled. So that's generally what the warning process looked like back on this day. And if there's one more point that I want to make, is the lack of lead time for the Huntsville tornado. We're gonna go back up here, and we're gonna see that the tornado warning was not issued until 4:35 p.m. The first report of a possible tornado was received at around 4:30, and additional reports were received at around 4:33. So this means that the tornado warning was not issued until about 5 minutes after the tornado had first touched down. This point isn't meant to bash anyone or anything like that, but it's a little surprising that there wasn't any lead time for this tornado, especially that this was such a well forecasted event. And so a vast majority of the fatalities came from this tornado, and have to wonder if the lack of lead time contributed to the large number of people killed. Maybe a possible explanation for this would be the limitations of radar. May not have gotten a full radar scan to be fully confident that there was a tornado ongoing. This more goes to show just how far we've come in the warning process, and that the significant improvements we've made to the system over the last several decades. And so that's going to cover it for the warning process on this event. And now we're going to take a deeper dive into the background environment and see how all the ingredients came together for this event. So going back to Tornado Archive, and we're going to look at the synoptic scale environment. And we're going to start at 500 millibars and look at the upper level wave pattern. And typically, I would like to start with 300 millibars to look at the upper level pattern, but the data sets that I would normally use don't go back far enough to look at things like the upper level jet stream or upper level divergence. But 500 millibars will do. We can still depict some things at this level. So we're starting at 500 millibars and looking at 12Z. So this is the morning of the event. And we have a pretty large long wave trough that is carved out through most of the continental United States. And so we also have a trough axis that is located from the upper Midwest down into the central and southern United States. And it's taking on what we call a positive tilt. So this is referring to the orientation of the trough axis and positive tilt. And so we have three different orientations. We have the positive tilt, which is oriented from northeast to southwest. We have a neutral tilt, which is oriented from north to south. And we have the negative tilt, which is oriented from northwest to southeast. So the main difference between these orientations is that with a negatively tilted trough, we're going to have stronger upper level divergence or diffluence, which is where your wind vectors are splitting apart, and it's going to create a void in the atmosphere. And so air is going to be brought up from below to fill that void. And that's where the synoptic scale forcing comes from for severe weather. So we're going to go forward through the day and watch how this trough progresses. So we're going to go forward to around late afternoon. This is 21Z or 3 o'clock in the afternoon. And that trough axis swings through the southern United States, and we also see an embedded shortwave that is beginning to emerge inside this longer wave trough. And so this shortwave trough is going to enhance the synoptic scale lift that is going to provide the forcing for severe weather. And so we can see some divergence at 500 millibars. We have winds that are coming from the south-southwest across the Ozarks and the Midwestern states, and then winds over the deep south that are more out of the west-southwest. And so that is creating some favorable divergence across the main area of concern. And so that's where the synoptic scale forcing is coming from for severe weather. And so we also have stronger winds that are coming out of the base of this trough here. That's just indicative of a very mature and organized storm system that is pushing through the central and eastern United States. And so going forward through the evening and overnight hours, that shortwave then begins to take on that negative tilt as it digs in to the southeastern United States. And so that's what our 500 millibar pattern looked like. Let's go down to 850 millibars and take a look at the mass response in the low levels. So we have our cyclone that is centered over the Great Lakes region, and our southerly low-level jet is going to be placed to the south of that. Our jet axis is located from about the Arctic region up into the Ohio Valley of about 35 to 45 knots or so. And as we know, the low-level jet plays two significant roles in severe weather. So here is the low-level jet. And so it is responsible for transporting warm, moist air to our target region, which is our warm air advection. And it is also responsible for increasing the low-level wind shear, which both ingredients are critical for tornadoes. So as we go forward, we're going to go see how this progresses through the day. And as you recall, the trough doesn't move a whole lot during the day. So our cyclone is going to stay relatively stationary until the overnight hours. So let's go forward here to about early afternoon, around 1 p.m. And the low-level jet axis shifts to the lower Mississippi Valley and the mid-south regions, and really begins to crank up where that high risk is outlooked. This significantly increases the wind shear and makes the environment much more favorable for tornadoes. And so by the evening hours, the low-level jet maintains itself ahead of the storms in progress and continues to transport that warm, moist air from the Gulf of Mexico. So now we're going to look at our surface pattern and see how that progressed during the day. So we have our surface low that is centered over Michigan. And it's kind of a broad surface low, but you got kind of a center up here in Michigan. That would consolidate as we go through the afternoon. We have a cold front that is stretching down from the Great Lakes down into the deep south, really. So this is a pretty large storm system. And now let's take a look at the warm sector here. In the blue shading here, we have low 60 dew points, and we have a pretty broad range of low 60 dew points on the morning of this event. So our low 60 dew points stretch from about the eastern half of Texas all the way east into Georgia and come up all the way up into the Ohio Valley. So this is a very broad warm sector and a lot of real estate to work with for a severe weather event. And so we're going to watch how this progresses during the morning. So let's go to late morning here. This is around 10 a.m. And if you have any experience in forecasting severe weather, you can kind of see why concern was increasing for a potential tornado outbreak. This is about an hour after they issued that high risk. And so you have mid to upper 60 dew points that are being transported here by southerly surface winds all the way up into middle Tennessee. And so that is very significant for a cold season setup. You don't often see this kind of warm sector in the colder months. And you also have some surface convergence ahead of the cold front. We have surface winds out of the south-southwest across Louisiana, Mississippi, and then winds more straight out of the south or a little bit out of the south-southeast across Alabama. And so we're going to talk more about this and why this was important in the mesoscale environment. But this is very concerning look during the morning hours. And so as we go through the afternoon, this is around 18Z, which is around lunchtime. Our surface low is beginning to consolidate somewhat over Michigan, and our cold front is situated from the Great Lakes region in Ohio Valley down into the lower Mississippi Valley. And so storms are going to develop along the cold front and ahead of the cold front as well, as the cold front tracks to the east. And so as that surface low consolidates, that cold front is going to begin to surge through the deep south and brings an end to the severe weather threat back to the west. And so that's going to cover it for the synoptic scale setup. Now we're going to look into soundings and the mesoscale environment. So I'm going to start off by pulling up an observed sounding from Centerville, Alabama at around 12Z on the morning of the 15th, which is located in the west central part of the state. If you're new to soundings and SKUTs, you should check out my video on understanding these kind of charts, as it gives basic information on how we obtain this data and what each of these lines represent. So taking a look at the SKUT, the first thing that I'll note is this very deep moist layer from the surface up to about 700 millibars. And so this is where the temperature and dew point lines are closer together and where you have the air is more saturated in this layer. And so above this layer, we have what we call an EML, which stands for elevated mixed layer. And so this layer consists of hot and dry air that originates over the desert southwest and that is transported to our target region by westerly winds aloft. And so that's kind of what we see here in our wind profile at this layer. And so this kind of a sounding is known as a goalpost sounding or loaded gun. And so we get this look by having our deep moist layer down in the low levels, and then you have your temperature and dew point lines split apart above that layer, and so that gives you what looks going to look like a goalpost from, say, a football game or something like that. Loaded gun sounding refers to an atmosphere that is fully destabilized, meaning that your partial temperature, this dashed line you see here, is warmer than the environmental temperature, which is the solid red line. And there's just a temperature inversion in the low levels that needs to be eroded, and the environment is then ready for storms to initiate. And here, for example, there is a temperature inversion at around 500 meters off the ground. And so that will need to be eroded for storms to initiate in this environment. And so that can be eroded by either significant warm air advection that's occurring in the background environment or any sunshine that we would get during the day. And so this moisture and temperature profile is pretty textbook for a significant tornado event. And so we can look at some of the instability parameters from this sounding. And so we can look at that by looking at the CAPE. Now by looking at the CAPE. So CAPE is located in this column, and that just stands for convective available potential energy. And typically we'll look at the mixed layer CAPE, which is at around 1,200 joules per kilogram. And so that number is pretty significant for a cold season event, especially down here in the southeast. We typically don't see numbers quite that high. So that's a very significant amount of instability, and also low-level instability. 0 to 3 kilometer CAPE is at around 90 joules, which is also pretty significant. You typically want to see that value at least about 50 to 75. That's going to be favorable for tornadoes. So that's what the thermodynamic and moisture environment looked like. Now let's take a look at the wind profile, which is not quite as significant for a tornado event. In the morning at least, you do have some variant of the winds with altitude, but you have weak low to mid-level flow throughout most of the atmosphere. And so that's also going to be represented in our hodograph, which you don't see a whole lot of curvature in that hodograph. And the hodograph is kind of short in the lower half of the atmosphere. This would improve, however, as we go through the afternoon, as that upper level trough approaches from the west, and that low level jet then begins to crank up in the afternoon. So we're going to watch how that environment progresses in the afternoon, but first I want to figure out what the storm mode for this event is going to be. And the easiest way to find that is going to be through the shear vector orientation with respect to the initiating boundary. And so this map comes from the SPC's Violent Tornado webpage, which is a good resource to use if you're looking to see what the environment was like back on days that produced violent tornadoes, essentially. So they have data that goes back all the way to like the 1800s, I believe. So plotted here is we have our surface-based CAPE and the 0 to 6 kilometer shear vectors. And so let's recall where the cold front is. which is going to be our initiating boundary. So the cold front is located from the Great Lakes and Ohio Valley down into the lower Mississippi Valley region. And so we're going to draw what our shear vectors look like with respect to the cold front. And you can see that they are pretty much parallel with the cold front, all the way up and down the frontal zone. And so that's indicative of a squall line that is going to be developing ahead of the cold front. So we have a linear storm mode that's going to be kind of the main show. And so if we're going to get any discrete supercells, we're going to need a boundary or other surface features to get that discrete storm mode. And so we're going to take a closer look at the surface map at 18Z back from Tornado Archives. Now let's depict and see if we can depict any surface features that could give us a discrete storm mode. So this is at the same time, at around lunchtime at 18Z. And so we note that there is a pretty noticeable prefrontal trough that is centered over central Mississippi. And so this is basically just a tongue of low pressure that is extending ahead of the cold front. And so you also note we have your surface convergence that we talked about earlier in the video, where you have winds out of the south-southwest across Louisiana, Mississippi, winds out of the south across Alabama. So you have this surface convergence near the Mississippi and Alabama state line. And that prefrontal trough is going to meet up with the surface convergence, and that can give us a discrete storm mode because the forcing along this boundary is going to be more subtle. So you don't get as many storms that go up, and so the storms will tend to remain more discrete. And so let's take a look at the shear vector orientation with respect to that prefrontal trough. So I'm going to pull that map back up, and I'm going to zoom in here a little bit to see over Mississippi. So this is approximately where that boundary is. And now let's draw our shear vector orientation with respect to that boundary. You can see that they are a lot more perpendicular to that prefrontal trough. And so this is also more indicative of a discrete storm mode that can be maintained ahead of the squall line. So forcing is going to be more subtle along this boundary, and we have strengthening deep layer wind shear in the atmosphere in a moderately unstable environment. So this is a pretty favorable environment for at least a couple of isolated supercells. Now let's watch how this environment progresses across Alabama, or in Mississippi and Alabama for that matter. And so we're going to look at surface base cape and look at the hodograph structure as well. That's analyzed from Tornado Archive. And I'm going to actually go back here to the morning of the event. So to recall, this is what the hodograph looked like back on the morning of this event. So you don't have a whole lot of curvature here in the low-level hodograph, maybe a little bit more here out of Mississippi, where closer to where that low-level jet is. And the hodographs are pretty small in the low to mid levels. So let's watch how that changes as we go through the day. This is as we go through the mid to late morning on the 15th, and then as we go into the afternoon hour. So this is at around 2 p.m. on the 15th. So you can see how the hodograph changes, and especially across Alabama and Tennessee, and really across the warm sector, generally speaking here. You got a lot more curvature in that low-level hodograph across Alabama and across Tennessee and even up into Kentucky as well. So a pretty favorable-looking hodograph, and also becoming more elongated as well as you go through the afternoon, thanks to that upper-level trough approaching from the west, and again, that low-level jet. So those things are critical for this significant tornado event to develop. And so this environment is pretty favorable for strong to violent tornadoes so long as we can maintain a discrete storm mode. So let's take a look at the radar imagery that's provided from the National Weather Service in their disaster survey and see if that was the case. And so this radar imagery begins at 2 p.m. and we have two discrete supercells where that prefrontal trough is located. 2 p.m. here is on this timestamp right here, and so this is the radar image at 2 o'clock on this top image. So these supercells formed along that prefrontal trough ahead of the squall line. And so this first supercell here that's labeled supercell number 1, this crossing the Alabama state line, and this is the storm that caused the Airport Road tornado. This first prompted tornado warnings for the west central part of the state, but there weren't any confirmed reports. And this supercell remained discrete as it tracked to the northeast towards Huntsville through about 4 p.m. This timestamp here is 21Z, which is 3 p.m. down here at the bottom. And so as we go forward here, to the next image. And so then some interesting things happen as storms cross over I-65 just after 4 p.m. So 4 p.m. is down in this bottom image here. Here's the timestamp for it, 22Z. And looking at the radar image, we have our supercell that is ahead of the squall line, but we also see this embedded Boeing segment here that's starting to show up on radar. By around 4:30 at the start of the Huntsville tornado, the Boeing segment and the supercell merged together here in this top image here. And so this still, however, maintains supercell characteristics, and there are some terms that we use to describe this evolution. One of them is called a line-embedded supercell, which is just a supercell that is just embedded in a squall line and still maintains the supercell characteristics and can still produce tornadoes. By 5 p.m. in this bottom image, you have storms that continue to track to the east across Alabama and eventually move into Georgia. You can also see some other discrete elements continue to develop ahead of the squall line and also form along another prefrontal trough axis that is developing across Alabama and Georgia. And so those produce the significant tornadoes across Georgia later that night that we saw earlier in this video. There's another term that we use to describe this evolution, but first I want to bring up this publication from French and Parker in 2012. And of course, I'll include a link in the description box below for this publication. And so these two authors studied the mergers between supercells and squall lines, kind of like what we have in our case study here. They also reference a paper from Goodman and Nupp in 1993, which specifically studied the November 1989 event. And they concluded that the merging of the squall line with the supercell actually spawned the tornado, the F4 tornado that tore through Huntsville. And so, as we know, supercells have an organized rotating updraft. So imagine if we have here a supercell, and so this is kind of a rough sketch. So sorry, this might look kind of cheesy, but just to kind of illustrate what we're seeing here. So the supercell is going to be ingesting warm, moist inflow from the surface, and that plus the strong vertical wind shear that is impacting the storm, this develops the rotation inside that supercell. However, this alone does not develop the tornado. Oftentimes, tornado will require an RFD surge, which is cool rear flank downdraft, that converges with that warm inflow from the surface. And so studies have shown that this often starts the tornado. In this case, that RFD surge came from the squall line as the supercell merges and the bow echo evolves. So I'm going to scroll down here to figure 7, and it shows the schematic of the types of Boeing evolutions depending on the background environment. So part B is going to best line up with the November 1989 event, and is called the embedded Boeing evolution. And it's characterized by strong synoptic forcing and strong vertical wind shear. And so, looking at the schematic here, we have our squall line here that's back out to the west, and we have a discrete supercell that is tracking to the northeast. The line breaks, the squall line breaks apart, and this supercell then begins to merge with the squall line. And you see the reflectivity notch here in the supercell, and it forms this embedded bow echo inside the squall line. This also represents what we call a line echo wave pattern, or loop for short. And so these loops, as we call them, is also responsible for producing tornadoes embedded in the line of storms. So going back to our radar imagery from this event, we're going to go back here to 4 p.m. You have our supercell here that's ahead of the squall line. And the squall line is going to end up breaking apart here. As you can see, a couple of breaks here in the reflectivity. And then as we go to 4:30, back on the 15th, this case strongly resembles this Boeing evolution. You can see the wavy look in the squall line here, kind of this wavy pattern here. And so when the supercell and squall line merge together, the gust front ahead of this squall line here likely produces enough RFD surge to likely initiate the tornado. And so there's another well-known case of this kind of evolution, and that is from the Super Tuesday 2008 tornado outbreak. We see this occur on multiple occasions, from all the way from Arkansas into North Alabama during the overnight hours of this event. And I'll take a deeper dive into this event on another video coming up here probably in the next few months, so stay tuned for that. So that's all that I'm going to have for today. Just for some closing remarks, I enjoyed looking back on this historical event to see how all the ingredients came together and look at how this tornado actually came into fruition. And so I hope you learned something and hope you enjoyed this video. And so that's going to wrap it up for this video. And thanks for watching. I'll see you next time.